Okay, I think it's recording now.
Okay. Is your screen like this?
No, because I'm sharing the screen, so it's mirroring. Let me like,
Oh,
yeah,
okay.
share once again.
Oh, oh, that's good.
Okay, so our first question is area of undeveloped. We actually don't understand
Um,
where to start to
okay.
measure.
May I know what do you mean by area of or undeveloped area?
Yeah,
May I know what do you mean by undeveloped area?
Doctor,
Yes.
uh, I, I answer the question.
Alright, sure.
The undeveloped area is such that has a mountain, right? That have ground level of the uh, ground level, right? So that the developed area is the road that we need to design to the
Okay. Okay. You have shared this screen, right? On your screen is actually the plan view of your
yeah,
proposed project. Okay. Imagine, right? There's no proposed road yet, so you have these hilly areas, all right, with which is denoted by the topography, right?
Mhm.
All right. Okay. Now you also have on bottom. You can actually see lot of buildings or houses, right? 8679, 8680, all those are lot number.
Yeah.
mm-hmm.
Okay. So then when you design it, when you propose it, you have given this alignment, the road alignment. Then with the road alignment and actually below this, the same drawing below it is the longitudinal section of longitudinal drawing. Um, which once you have given the horizontal and also vertical alignment, this will be produced where based on the vertical alignment, whether to cut or fill the area. So therefore you have all these tadpole thing. For example, on along chainage from chainage 275 to chainage 375, you actually have left and right, you have cut sides slope, and then for example on the left, when I'm actually moving from smaller chainage to larger chainage, my left is the one which has more than 12-meter cut. Why I said more than 12-meter cut when I measure vertically, right? More than 12 meter, because if you look at that, you have two bench drains there. All right, so
Mm-hmm.
it's more than 12-meter. And on the right side is actually less than 12-meter because you only have one bench drain. All right, if you can see that. All right, so now I believe when you say it's undeveloped area, I believe you said is you meant what do you mean is the drainage or catchment area that will be draining, the area that will be draining into your drain. Am I right?
Yeah.
Okay. Now let's go one by one to your question. Can I share my slide right
Oh,
now? Okay,
sure.
great. Just a second, presentation one. Okay. Oh, wait. Oh, I think I didn't save this guy. That's why. Are you guys going anywhere? What I mean is just staying home, is it?
Yeah, we are at home.
Alright. How come I cannot present? Okay.
I already stopped presenting.
Oh, you already stopped, huh? Okay.
Yeah.
Okay. Just a second, I need to present this, then I need to stop, then I present again.
Okay.
Okay, presentation 3. Okay. Now you should be able to see my screen, right?
Yeah.
Which is the I have a list of your question here. Okay,
Mm.
and I think just a second. I'm going to do slideshow now. Okay. You have given me 6 questions lah, basically.
Yeah.
I believe your area of undeveloped should it I believe the area of undeveloped, what you mean by area of undeveloped is the catchment or drainage area. Okay, later I'll explain to you. Okay, the next question that you want to know is how to find overland sheet flow, right? Path length, which is L0. And then the third, it would be slope of overland surface. Then you have friction slope, length of ridge, and then storm duration. So let's go to the first question that you are asking, which is the catchment of drainage area. Now, let's look at this first, because we have to get the concept right. You have this catchment. You have now. Let's go to your drawing. Okay, this one. Okay. Now this is the drawing, which is a plan view. That means you are looking from the top. Okay, that means top view lah. All right, looking from the top. If you read the ground level points, right? You have 82.24. You have 83. Then you realize that this top part here is actually higher ground. That means it's kind of hilly area where the elevation is going down. All right. So now if I put it in 3D view, okay? 3D view, you are going to have, when you are looking at 3D, right, it's something like this lah. This is just an example. I wanted to explain how you are going to get the boundary of your catchment area. All right. So now let's imagine, right, you have rainfall coming down. You have it's raining. Now imagine how the water is going to flow. The term that we use is rainfall runoff, where the rain runs on the land. All right, so it's termed as rainfall runoff, right? Now, what is the direction of your flow? It's going to be like this. Now, of course, when you have flow, is going from higher ground to lower ground. Okay, this is the direction of flow. Now, here's the thing. Look at this, how you are going to delineate the boundary. If you look at this, the boundary would be the higher ground, because it's actually separating the direction of flow. This part here is going down to the left, and this part here is going down to the right. Now, of course, depending on the elevation of the ground, right? If you look at this, right, this of course is going to be that direction, and here, this part here on the top part, right, or upstream part, right, is going to the other pond, all right, or other body, right, which has lower ground elevation. Of course, this part here is coming down.
I'm sorry, doctor.
Yes.
We can't see your cursor.
Oh, you can't see my cursor. Okay. Then
Okay.
what I should do is I full preview. Then I'm going to use pen. Okay, or laser pointer. Now, can you see my cursor now?
No.
No. Okay. Let's look at my pen. How about this if I draw it?
No.
Okay. I'll try. Okay. I'll try to do. I'm going to start presenting. So I'll try to present entire screen. Okay.
Right.
Okay, if it's entire screen. Now, could you see my laser pointer now?
Yeah, we can see now.
Okay, great. Okay, now when I mentioned, when it's raining, right? Okay, if it's raining, this would be the direction of your flow. All right. So far, so good, eh?
Yeah,
Guys?
doctor.
Yes,
Yeah,
yes.
doctor.
Okay, clear. So, this part here is the highest ground, right? Correct? This is highest ground. And of course, right, when rain falls, right, the direction of your rain runoff, right, okay, would be, for example, this part, right, this has a bit a depression here, so it's going down to this area here, whereas this part is flowing out here. Now, let's say if I want to determine the size of a drain, okay, located here, which is denoted by the red circle, okay, I want to determine the size of the drain. How much, what is the size of the drain? Now, before I determine the size of the drain, I need to know how much flow that I need to cater. Now, how much flow that I need to cater, I can actually determine from how much rain or discharge due to rain that comes in and flow out from that drain. So how much is, of course, you have, rainfall intensity, you times the area, you are going to get how much discharge from the rain. That is why you use this rational method. That means you have I times A. A is the area that will be draining. That's why the term drainage area, the area that will be draining, okay, out of this outlet here. Now, I know your rational method formula is Q equals to CIA. Okay, later I'll explain on that. Okay, now imagine everything all the rainfall, right, that comes down touching on the land will flow out. So I have I times A. If, if there's water or the rainfall goes into the ground, that means you have seepage, right, or being evaporated. Okay, that means it is less than I times A. I is rainfall intensity and A is the drainage area. Of course, C would be the land use coefficient. Land use coefficient equals to 1 means everything that comes down from the rain will go out from here or being discharged basically. But if there is some interception due to seepage or being, you have depression that, stored, the rainfall runoff stored in the depression, then your C would be smaller. Therefore, your Q would be smaller than I times A. So, if you look at, manual Saria Mesra Alam, right, or the Urban Stormwater Management Manual, C depends on land use. If you have, pavement, your C value is higher. If you have forest, land cover, your C will be smaller. That means more rainfall runoff will be intercepted. Okay, now, divided, I hope by now you should know why your rational formula is divided by 360. It's just you convert your A, the area, from hectare, and you convert your I from millimeter per hour. You convert it, you divide, that means you are converting it into cubic, right, or meter cube over second. So therefore you divide it by 360, you'll get meter cube over second. Now, let's look at this. This is how I delineate the drainage area or the catchment area. Now, how did I do that? You see, I look at the direction of flow. I said, what is the area when rain falls that will be drained out from this red circle here or the outlet here? I imagine when rain falls, right, the direction of flow, for example, I use pen. Here it would, let's choose other color. Right. Here it will flow, probably here I look at there's some depression, it will flow out from there. Here, of course, it will come down like that, it will flow out like that, okay? So I imagine only this area that when rainfalls touch on this area, it will be drained out from this outlet here, okay? So it will go like that, it will drain out. So this dashed line here is my catchment area, and I need to find this area here for me to use in rational method. So far, are you guys clear? Hi, hello
Yes,
guys.
doctor.
Okay, you are clear. Now, from this concept here, okay, we will be looking at this plan here. How are we going to get it? Okay. Now, how are we going to determine the catchment area? So by now, you should have you should have been able to label or identify type of drain. You have interceptor drain. Actually, the name of it, right? Interceptor drain. That means it intercepts rainfall runoff from upstream, from going into the other drains. That means, the drain that will rain on this area here won't go into bench drain because you already have this drain interceptor that intercept all the runoff from upstream here. Then you have bench drain. Bench drain, the drainage area is just this area here. You have another bench drain. This bench drain here, the drainage area is this part here, because when rain falls on this part, right, it will drain into this bench drain. Then depending on the slope of this bench drain, right, for example, if it's flowing from left to right, then the water will be flow out into the interceptor drain. It won't go into the bench drain below it. So the bench drain here, the area of drainage is this part here. Okay, so this part that will be draining into this drain here. How about roadside drain? Roadside drain, you have two areas. One from the cut slope, this part here. The other one is from the middle of the road. Let's do this. Of course, if you want to design the interceptor drain, you also have to account for Q coming from this bench drain and Q coming from this bench drain here. And of course, if you have sum here, then you don't have, that sum also have to consider Q from interceptor drain and Q from roadside drain. Okay, now let's draw this out. Okay, now what I was explaining just now here, you have bench drain. You see, when the rain falls, right, it only cater for this drainage area, because you already have interceptor drain that will cater for the upstream land. Another bench drain, only this part. Of course, this is cascading drain lah. It doesn't matter. We are not looking at that cascading drain. So far, okay, guys.
Yeah.
All right. Now, let's look at this again. So what I'm going to do is I'm going to draw out. Now, imagine you want to determine the catchment area for BC, which is the bench drain, right? What I could do is I said, this. So this blue area is the A, drainage area into the bench drain. Now here's the thing, this is a plan view. You are looking from the top. In reality, this is the area that you are encountering. Let's go back here. This is I'll just use pen. This is the area that you are considering that will flow into this drain here, this bench drain here. Now, from top view, we only, the dimension that we are going to see only, of course, the plan dimension. But in reality, the area is actually larger. Do you agree with me?
Yes.
Because of the sloping, right, area. So your A, you should consider, depending on the cut slope, you should consider the slope lah to get the larger area. Okay. Now, but I don't mind. Okay. I don't mind if you just, want to, for the purpose of just learning, you just get the plan area. But of course, this is the limitation that you should have written in your report. How you get the area, because when I interview or when your lecturer interview you during assessment later, you should explain how you get it lah. Now, the tough part would be to imagine how you are going to determine the catchment area for the interceptor drain. Okay, because it's not so direct. Okay, now let's draw it out. Okay, let's draw it out. Imagine, I said imagine. I said maybe the top part here is going to flow into the other direction, but eventually it will flow down here. Okay. It's up to you, but you have to justify how you are going to get this area here. Okay. So I have here. Okay. I imagine, the flow from upstream here, it will go down. Eventually, it will go down here. Okay, but not so. I just something like this. All right. So I have. So this will be the area. Now this is what I have delineated for my catchment area that will drain into this interceptor drain here. So this is my A. Now, how would you determine this area here? By now, I think when you show me your slide just now, I think you have already know how to determine this area, right, on plan?
Yeah, we already determine our own area.
So because between this section here is 25 meter, right?
Yeah.
So you can use your dimension on the plan and convert it into the real distance. So this one you could, roughly estimate it as a triangular, okay, and then you minus another triangular here. So you are going to get this lah, all right, area. So, okay, does that answer your first question?
Yes.
Okay,
How about
that's good.
Victor? Victor, can you say something? Because Victor.
I got a internet problem. Wait, I cannot see the slide.
Oh, you cannot see the slide,
I got internet problem, I think.
Okay, but how about your friend? Can you see the slide?
Yeah, yes.
Okay, now here's the thing, there's another part, but it's okay because this is being recorded, right?
Yeah.
So you are going to see it for this part here, right? Okay, I'm going to enlarge it a bit. Okay, for this drain RSD, right? You need to consider two part, because first, okay. First, the area, that will go into the roadside drain, and then do you think there's another area that will drain into the roadside drain also?
The road.
Yes.
Yes, correct. Okay, it's the road. So you are going to have another area from the road. Okay, so then maybe I put like that. Okay. So this is the area. But remember, the land use coefficient for, this is only half of the road, the land use coefficient from the road is different from the land use coefficient, because here you consider turf, right? You consider the cut, like this is turfing, you have grass, right, cover, whereas the road, the cover would be pavement. So it's different. I think it's 0.95. This is maybe 0.55 or 0.6. See, so therefore you expect this, if given the same area, right, this would have larger queue compared to this, but you have to combine them in order for you to design roadside drain. Now, here, let me go back to this, how you are going to look at this guy here. Now, imagine you want to design this this interceptor drain. Okay, this one I bring forward. You want to design this interceptor drain. Okay, here's the thing. Have you ever seen road or a drain, the design where upstream small, then coming to downstream large, the size? Have you?
Haven't.
Yes or no? That
Haven't.
means,
Haven't seen.
yes, haven't, right?
No.
It's constant size, right? Agree? The size is constant,
Yeah.
right?
Yeah.
So
Yeah.
when the size is constant, definitely you say you want to design the part where it has most discharge or peak flow. Where is it? Okay, assuming I don't know the direction of flow. You have to determine the direction of flow in the drain. Assuming, okay, the flow is like this. I'm just assuming, I don't know whether it's correct or not.
Okay.
All right, in the drain, this is the direction of flow in the drain. I should put it in the drain, okay. Okay. Okay, assuming this is the direction of the flow in the drain. So now, therefore, okay, now when you consider this area, right, you need to imagine what will be the area going to the left and right. So, okay, now I said, okay, I think what I'll do is I'll do this. Assuming that direction, I just take up this part here. I see, maybe yellow. Okay. Now, if you look at this, I draw another catchment area. Since that's why I think in my video, right, I explained that you need to determine the direction of flow in the drainage first. Why? Just now, if you consider the whole interceptor drain, right, this would be your catchment area. However, if you consider the direction of flow in the drain, right, that means you need, okay, between left, because the direction of flow split into two parts going to the left and right. So that
Doctor, I think your mic just off. We can't hear you, Doctor.
Doctor, 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 can you hear me?
Hello?
Hello, doctor.
Yes,
Eh,
doctor.
how come just now?
No,
We cannot hear you.
Oh, okay. Either your maybe my internet is not very good too. Okay, can I
because
share?
your mic is off halfway when
Oh,
you're explaining.
really? Okay.
Yeah.
But are you able to see my screen right now?
Yes, doctor.
Okay, now okay. Now are you clear that you want to design interceptor drain, right? You should, consider the direction of flow first, then you are going to determine the catchment area. Just now, if you don't consider, right, you'll take the whole catchment area, right? But if you consider the direction of drain, for example, the drain on the right hand side, only this catchment area. Because on the left hand side, the remaining area will be draining into the left hand side. But of course, you need to compare, see which queue is larger, then you are going to use the larger queue, the size, to construct for the whole stretch of interceptor drain. Is it clear?
Yes.
Okay, great. So here's the thing. There's another thing that you need to consider. You see this? Let's use this, change. You see this bench drain, right? Depending on the direction, let's say it flows from left to right, right? There's a queue here. Am I right? Queue from CIA, right? That will go into the interceptor drain, right? So you also need to consider that queue, in order to design for, to get the queue peak here, because it's flowing into the drain as well. Okay, because you don't want to design something that you only consider the upstream, but whenever the flow coming from this cut slope area, you cannot cater for it. Okay, guys, okay, so far?
Yes.
All
Yes.
right. So therefore, I answer your first question already, right?
Yes. So I have one more question for this one.
Okay.
As you said, right,
Mm-hmm.
we are looking from the plan view.
Yes,
So
correct.
we are calculating the area from the plan view only, right?
Correct. Which is smaller?
So in our project, we are only calculating our plan view. Or
Suppose lah, you need to consider for the slope. So you could, look at, you have this point, right? You could tentatively assume what would be the slope, then you divide it by the slope, or you account for the slope, then you will get larger catchment area. Is it
oh,
okay? That's better. All right. As
okay.
engineer, you should consider for that.
All right, all right.
Okay, which is safer lah. Okay. All right. Any more question for your question one?
Doctor, can
Yes.
I ask about, I was confusing about the area of the catchment area that the doctor used the red color one.
Okay. This
We,
one.
we combine it from the vertices to the vertices from the slope, right?
Uh, you combine it. How you are? That means your question is, how did I determine the boundary? Is it?
Yeah.
It's based on this. Look at this. When you need to imagine when rain falls, right? The drain that will be draining out from this would be this area here. Therefore, this would be the boundary. Okay, let's go back here. That means when rain drops on this part here, okay, this point here, whenever rain, just a second, I think I'm going to mark, okay. That means whenever rain falls on this area, okay, it won't go out from here. Only, this area, when rain falls on this part here, it will come out from here. All right. So that is how you determine the boundary. So let's look at this one here. Okay. How do I determine the boundary here? Is I use a different color. Is okay. I imagine when rain falls, the rainfall runoff direction will be like that. Then eventually it will come into like that. Here, I imagine it's going to be going to that area that would not go into this drain here, interceptor drain. So therefore, this is how I determine this area. Now by right, if you go back to this slide, right, by right, look at this. This is the highest point that would, you say when it falls, the rainfall falls on the other side, it will flow into the other side. And when rainfall falls on the left side, right, it will flow, all right, to the left. So that's how you determine this boundary. It's actually the highest point. For example, you compare left and right, this is the highest point. Here, this will be the highest point, this part highest point. We say it's highest point because this will separate the direction of flow. Similar to this, all right, you need to assume, okay, so imagine this is the highest point, right? The flow, oops, sorry. Oh, what did I do? All right, I think I pressed the thing wrongly. Okay.
So doctor, we just estimate the area, right?
Yes, correct. You need to imagine the direction of your rainfall runoff, then you can get the boundary. By right, you would that's why sometimes people say, you need to look at the highest point, because actually the highest point will separate the direction of rainfall runoff. Are you clear?
Yeah, doctor. But I have a question about this. This is a left side. How about the right side? Because the right side is for the residential area, right?
Okay.
So we don't know the rain, how the rain flow to the drainage.
Okay, here's the thing, Okay. I'm going to discard this. I'm going to come back. Okay. Okay, here you have points 76, 77. You have this ground elevation, right? Given, right? 69, 67. You agree?
Yeah,
Okay.
yeah, agree.
Okay, so when rain falls, okay, this would be like that. I don't know which you have. I think yours is you have more, right? Point. I snip this. Okay. So for example, this interceptor drain here, okay, you could consider this area here. Now, here comes to one, when you ask this question is good too. When we design this, okay, sometimes we don't have sufficient survey point. Why? You don't expect the surveyor to give you all the points, because you have given them the scope of the area that they will do survey. The larger the area, more expensive of the surveying fees. All right. So imagine you have this. You wanted to know what is, for example, here. You wanted to know what is going on upstream. Do you have higher ground so that you can consider more area of drainage area, or after that you have lower ground? That means you don't have to consider. So you need to do site survey. go to the field, look at what is there. Sometimes, for example, you have pylon. Pylon, you know, this tiang electric, right? Okay, that block your way. So when you design this road also, you need to make sure it's out of, your alignment is out of that pylon pathway. All right, so you have to be careful. So that is the importance of your site survey. Clear?
Clear, doctor.
All right. So this one okay, eh? You have this, for example, I draw this out. You can consider this your catchment area, because you said, apart from this boundary, right, away from this boundary, the direction of flow probably will flow into another outlet already, but not, the outlet that you are considering. For example, this one, maybe you have one outlet here, the other outlet is here. So you need to consider what is the area draining into this and what is the area draining into that. Clear?
Clear, doctor.
Okay, like this, you need to have this and this. Okay. All right. So I'm going to stop this. Do you have any question, or we go to the second of your question?
Doctor, do we
Yes.
need to calculate the C average?
Sorry. You only need to calculate the C average if, for example, this area one catchment area consists of more than one land use type. Then you need to calculate C average. If one land drainage area that you consider has the same land use, you only use one, right? Agree?
Agree.
Okay. Or sometimes, for example, when you have two different, are you still looking at my slide?
Yes, doctor.
Okay. Sometimes, right, for example, you have, let's see, you have this part, for example, residential area. This is industrial area. This is hospital. And then you have lawn all around. Therefore, you need to calculate this area, okay? And then determine the C, calculate this area, determine the C, calculate this area, determine the C, calculate the lawn area, okay, of course minus this area, okay, determine the C, then you can get your C weightage C, but it's actually not C average, but C weighted C, where you have C1A1 plus C2A2 plus C3A3 divided by the summation of all A lah. Alright, A1 plus A2 and A3 and so on. Is it clear?
Clear, doctor.
Okay, that's good. Okay, what else?
No.
Okay, no more. Okay, so let's go to the second of your question. You asked for overland sheet flow path. Okay, can you show me your formula for this? I'm going to stop presenting. Okay, show me your formula from your MASMA.
Wait, doctor.
Okay, no worry.
So we are going to share our screen, right?
Yes, correct. I already stopped sharing mine.
Okay. This one?
Okay, yeah. Okay, correct. Now, Wei Tek and Yong Han, I have one question. Why do you need to find overland flow, or the travel time of overland flow?
Um,
Okay, you have your Masma, right? Okay. Could you search for the term time of concentration?
time of concentration.
Yep.
Nope.
It's actually
Oh, you mean from this PDF?
yes. Okay. Go to, how should I say, 2.1 introduction or page 2-1. This one. Okay, you already have this, right? If you look at this, right, it says time of concentration is the travel time of runoff flow from the most hydraulically remote point upstream in the contributing catchment area to the point under consideration. Okay. Now, the practice, okay, I'm reading from the first paragraph, last sentence. The practice is to select the design storm duration as equal to or greater than time of concentration. So, do you still remember in your rational method you have QCIA and your I, in your I formula, you have a duration variable there?
Yes.
D, right? So now do you know your D should be equal or greater than TC?
Greater.
No. I mean, like, it's either equal or greater, but you can use equal. It doesn't matter. It's either one you can choose. Are you clear?
Clear, doctor.
So therefore, how do you find the time of duration to find rainfall intensity is you need to find TC first, because you say you want to use your D equals to TC. Clear? So far?
Clear.
Okay.
Yeah.
Now, the second paragraph under 2.2, it says TC is the summation of T naught, TG, and TD. So basically, TC is T naught plus TG and T plus TD. Now, if you want to design for road drainage, okay, are you planning to design for road gutter?
No, doctor.
Okay, if no, TC is only T naught plus TD because TG is 0, right? Agree?
Yes.
Okay. So here's the thing. Now, let me explain something. Why you need TC? Can I open a? I can. Can you stop sharing because I want to draw something up. So
Okay,
I want to
done.
share my slide right now. Okay, Vixena and Telescope. Okay, you should be able to see my screen right again.
Yes.
Okay, now let's go back to this slide here. Okay. All right, I want to find TC. What is the importance of TC? Okay, by now you should know TC is okay. It's okay. I want to actually just a second. You can see my slides, right? What I'm doing, Ken?
Yes, doctor.
Okay, great. So TC is time of concentration. Let's try to understand what time of concentration is about. Now, okay. Right. What is it? Okay. The word, okay, it says time of concentrate. That means the time needed for the flow to concentrate. Now, to concentrate on what? Now, here we consider the outlet. All right, this would be the outlet. Time for all the flow to concentrate at the outlet. So we need to find the time, okay? Right. Now we say, all right, so I'm going to enlarge this a bit. Okay. Okay. Now the time to concentrate at the outlet here. Now, if I were to draw a graph, okay, oops. Sorry, the graph is smaller. Let's try to understand what TC is about. Okay, on my x-axis I have the time. On my x-axis on my y-axis I have the discharge Q. Now this graph here I plot for is the hydrograph that I plot for at the outlet here. Now, here's the thing. When rain falls on this area here, the the Q that will come out from the outlet, okay, I imagine, all right, so, sorry. How come? Okay, I imagine the water that will come out from the outlet is just from, the area. For the first minute, the area that will be draining out from the outlet at the red circle here is the one that I draw, the boundary within this area that will drain at the outlet. Then after that, of course, during the first minute also, this part here will only flow from top until this area only. Then after that, all right, of course you have water coming from here to here, here to here, here to here, all right. After that, after some more minutes, more area will be draining out of our outlet. Would you agree that the Q at the outlet is increasing? Agree on that? With time.
Yes.
Okay. Increasing until, all right, at a certain time, all the flow from all this catchment area will be coming out. Okay, provided the rain never stop. Okay, rain never stop, and rain, of course, we have been assuming that rain falls uniformly over this entire catchment area. So until at the point where all this flow runoff concentrate at this outlet here. Therefore, after TC, the Q would remain constant that would come out from the outlet. Agree or not?
Agree, doctor.
Okay, so therefore, this is the meaning of time of concentration. Now, why does, they say TC is equal to T naught plus TD plus TG. Okay, now, overland, drain, and gutter. Here's the thing. Assuming I have a river here, okay, a river. Okay, this is the river, all right? So I need to find the time, okay, because the formula that I use for the time that drains into the river is I need to find the time of TD, because it's TD is any open channel. It could be river, drain, or any open channel form. And then overland is the time taken for the runoff to flow over the overland. Now, just in case, right, if you, here's the thing, if the time, right, for the overland flow, if everything comes into the river, then flow out is good. That means you have T naught plus TD lah, because if you use this formula, it's fine too, because TG is definitely 0 already. Sometimes you can only at times, right, sometimes there's no TD, that means there's no river, so you only consider T naught. Sometimes it's TD only, because everything flows into the river, then you consider TD. Now, when I said that, actually you can get a lot of TC, a few combination of TC. Which TC you want to use? Of course, the largest TC, because you said that when the largest TC, all the flow will concentrate. So you have to choose, a few pathway. You need to imagine first it will flow from the highest ground out into the river, then you consider TD. You consider T naught, TD, or you consider TD, then it will flow. That means according to the topography, it will flow along the drain, but it never goes into the river. So you have 100% T naught. You need to compare all those, okay, and then you find the largest TC, because when it's the largest TC that you choose, definitely everything is going to concentrate at the outlet already. But for your project, don't worry. You just, you take one or two, as long as you can justify or explain in your report, is fine. You said you are assuming, this part is, you consider T naught, then TD, then it's fine already. Are you clear with that, guys?
Yes.
Okay. If you are not clear, you need to ask, Okay. So, do you have question then for question number 2? Okay. Actually, I haven't touched on L naught, Okay. What would be L naught? Okay. Now, L naught would be this. If you said, right. Just a second. I think I need to use. You are still looking at my screen, Ken?
Yes, we are looking.
Alright. So, assuming, Okay, so I'm going to have another different color. Okay, you see the yellow line, right? Assuming that is the pathway where the overland, the runoff flows on the or runs on the overland. So I need to find the time for this. In order for me to find the time, I need to know the length of the pathway that it flows, alright? And determine the slope. Now, how are you going to determine the slope? Of course, you have invert level, right? You need, for example, you have, sorry, not invert level, you have ground elevation. You need to get, you know, the ground elevation in any 2 points. You are just assuming, right? At any 2 points, you can get the gradient of this slope here. Then the length you can determine on the plan view or plan drawings, and then you have to account for the slope as well lah. You can get the length of the overland flow. Clear?
Clear, doctor.
Okay, so that answer for question 2 and question 3, am I right?
Yes.
Okay, so if that answer for question 2 and 3, let's look at expression slope and L. This is the slope and L for the drain to find TD, am I right?
Mm-hmm.
Okay, for this drain here, right? Okay, here's the thing. For this one, if it's river, of course, you need to look at the invert level of the river and also the length of the river. But okay, let's go back to this one here. Let's assume this drain, you are going to design this BC, Okay, now you said I said the longest would be, or how about this part here? This is easier. Okay, this BC I want to design. I said the longest is going to take me is this pathway because it's larger, larger land overland that it has to go through. Okay, then okay, I would like to draw this. Then it would go from here to here. Assuming the direction is left to right. I don't know. You know the direction of flow because you have analyzed it. But I'm not sure how do you analyze it lah. Format painter, touch on this. Okay. This is where I get my T naught. This is where I get my TD. Now, how am I going to get, of course, the length, you should be able to estimate already, right? Using the scale. How about the slope? Okay, let's look at our slope, All right. Do you know how to determine the slope of your drain? Guys? Yes, no?
Yes. Yeah.
Yes. You have already determined. Okay. Let's just, I think I close my you see, I have given you, right, at every chainage, I have given you cross-section. This one, right? I have given you cross-section.
Yes.
So let's look at chainage 325, 350, and so on. 325, 350. Okay, yeah. Okay, yeah. All right, so I'm going to enlarge this. 325. Now, this is on the left. This is our road. If you look at from the top view, of course, you are seeing this top view, right? So this is the left, right? So let's look at chainage 325. Chainage 325, Okay, I have, if you look at from the plan view, I have one bench drain, one roadside drain, another roadside drain, another bench drain, another interceptor drain. Okay, here there's another interceptor drain too lah. Okay, let's look at chainage 325. This is the part where interceptor drain is. This is where bench drain is. Because if you look at the scale, right, this is 6 meter. Alright, if you read it from here lah, it's 6 meter. Because you know this is 5 meter. Okay, so it's 6 meter. Alright, now bench drain, this is roadside drain. This is your road. This is cross section, along chainage 325. This is roadside drain, another bench drain, another cross interceptor drain. Now, how would you know the slope of your drain? Let's look at this bench drain here. Now, this is the bench drain. The invert level, okay. Now, of course, this is existing level. That means this is this level here. this is the finish level. That means this is the finish level. And offset. Offset is offset from the center of the road. Means center of the road is 0. When offset to the left is negative, offset to the right is positive. So let's look at this. Let's look at this bench drain here. The input level, we are just reading from finish level, is 73.69. Here, now, this is the corresponding bench drain and not this one. This one is another bench drain. This one will connect to that bench drain because this is the first bench drain after the first 6 meter from the road, measured vertically from the road. Then you have 74. So 73, 74, you know the direction of flow is from change 350 to 325. Okay, I'm just looking at one drain. Okay, you have another, here you have 1, 2, 3, 4 drains. Okay, then change 375. Okay, this bench drain here is 74.75. Okay, this is higher ground, so still going to the other direction. Then after that, you need to read change 74.75. This one is 74.829. Okay, then 74.4. Okay, then what else? Okay, no more. So if you look at this, the direction would be is actually the other way. Is from that means this direction of flow is like that. Do you guys agree?
Agree, Doctor.
Oh, sorry. Just now the bench drain that I'm looking at is this one here. This is the first bench drain. Am I right?
Okay.
Yes,
Yeah,
doctor.
okay. Because I said I'm looking at 3 to 5, right? This is the bench drain. But let's look at 450 and 425. I suspect this is going the other side. Okay, let's look at this. 450 and 425. Okay, here. So I have this 74. If you compare it, one is 74.829, the other one is 74.493. So it's going from 425 to 450. So I need to compare 400 with 425. Okay. So where's 400? Okay. So this is the other side. Okay. 74. Okay, so now this is going to the other direction. This is going to the other direction. You need to help me check. I'm not sure whether I got it correct or not. Am I right? Is it 425 or 450? Oh, it's actually okay. It's actually 400. 400. Okay, separating at 400. It's here, right? Agree, right?
Yeah, doctor.
Okay. So what you could do is you actually can do this. You put a circle there. You said this is the separation lah, alright, of the direction of your flow. So you would know. You would know, right? I could do this. Okay. Because if I want to design for this bench drain here, what I'll do is I would consider there's one catchment area here. Okay, and there's another catchment area here. Okay, So I have two catchment area here. Okay, I mean one is for this outlet, the other one is one is for this outlet and the other one is for this outlet. Okay. Okay. So far so good, guys?
Yes.
Okay. So now you know how to determine the slope of this drain already, right? The slope of the drain is actually you need to compare this. For example, right, I can determine this slope from 400 to 425. I take the difference of the finish level. That means 74.922 minus 74.829 divided by 25 meter. Agree, 25 meter because the distance between it is 25 meter.
Yes.
All right. Okay. So, all right. So I have answered one up to 5. Then, the storm duration I already answered, which is TC. You agree?
Yeah, doctor.
Okay. Which is
Doctor,
T1
do we
yes.
can we use the storm duration greater than that, right?
Can.
But we just put a number greater than that, can?
But how much you are going to put? So it's easy to estimate it is equal to TC. Agree? Guys? It doesn't matter, but because this one, I think I show you the concept why you need to find TC, right? Agree? Because it's the time taken for all the flow to concentrate at the outlet.
Yes.
So if you agree, okay. Now here's the thing. You know that you need to compare Q rational with Q Manning. Am I right? You are using Manning kan to find the because okay. My question is, which one should be greater? The Q Manning. Q Manning is based on the section of the drain that you design. So which one should be greater, Q Manning or Q rational?
Q Manning.
Correct, because your
So
size
so
should
the
cater for the drain coming from the drainage area. Okay. So,
yeah.
okay. Now, can I have another thing to mention here? Do you know what is the okay? Just now who showed me? Is it Ho Yong Han that showed me the paragraph of time of concentration, the text?
Yes.
Can you show me again? I have another thing to explain. You are presenting, is it?
Yes, doctor. I
I
send it.
couldn't see anything though.
Same
No.
doctor.
Okay. Good. Okay. This one is okay.
Now?
Yes. Go to the next page. Okay. I want to see the top part. Okay. What could you read? Could you understand the last line?
The recommended minimum time of concentration for catchment is 5 minutes, which applies to roof drainage.
So what does it mean? You cannot use TC less than 5 minutes, huh? Okay? It's fine.
Okay.
Okay, minimum 5 minutes. Okay, now I need you to find another page. You can search for conveyance facility. Conveyance, facilities. Try conveyance facilities. Next. Click next again. Okay, here. Okay, could you go to that table, surface flow criteria? Now, here's the thing, look at this, it has this limit, flow velocity. For soft line means grass, okay, or earth drain. For hard line means concrete, okay, whatever material that you have been using, okay, or rubbles, you have to make sure your velocity is less than 2 or 4 meter over second respectively when you design, because remember, you have already have slope, or you can determine the slope of the drain. You need to make sure this is your last checking. Once you have checked Q rational is less than Q Manning is okay, then you need to check for flow velocity in the drain. Make sure it's not greater than this. If it's soft line, make sure it's not greater than 2, and hard line not greater than 4, because you don't you want to avoid erosion. And actually, erosion, and actually there is a minimum limit too. I forgot where is there's. You need to search lah. There's a minimum limit too. Why there's a minimum limit? You want the flow to flow, and you don't want it to pond that cause build up or sedimentation, things like that. There's a minimum to somewhere. Okay, you need to go through lah. Is it okay?
Okay.
All right. So does the session helps?
Yes, doctor.
Okay, that's good.
Doctor, one more question
Yeah, sure.
about our
Oh, that's good. You have done a lot.
for our bench drain, right? For the
Yeah.
Manning roughness, we are not sure the value because it doesn't say anything. Just take concrete.
No, it's glazed earthenware. There below
It's
the
not.
you know what is earthenware, right? You
Oh.
remember seeing drain which has this dark brown color? That is earthenware. Okay. It's glazed, alright? Glazed, it's kind of smooth surface lah. You can actually search for Manning. It's Manning. It's probably not here. It's probably not here. Actually, I'm not sure whether it's almost similar to this vitrified clay or not. We can use that. This vitrified clay, the pipe material below it, the vitrified clay, check whether it's similar or not. Okay? Whether you can use.
Alright.
You need to check. Okay?
Doctor, the one more question is the same as the bench drain. The given value is for radius or diameter?
Which one can you show me?
This one.
Okay, can you increase it?
I'll show a clearer
Okay.
image.
Okay. Okay, your question would be?
The value is given in radius or diameter?
This is half round. This is the width, if I'm not mistaken. 200 millimeter half round. The width means the diameter.
All right, doctor.
It's diameter. Could you go down the page and see? Is it anything written there? But I believe it's diameter lah. It's the width given there. It says no, nothing. Bermula mesh half round base at the mesh and content. 300 you see. It should be diameter lah, because it's actually the width. It's the width. The width should be diameter because it's half round, right? So it's the diameter lah. If it's radius, that means is the width would be 450, which is quite large already. So it's a diameter. All right.
All right, doctor.
Okay. Any more?
I think that's all. How about Victor? Do you have any question?
I think no already.
Okay, that's good. I'm not sure who's recording this. Could you share this recording with me later?
I'm recording, so I'll email you.
Okay, great. Thank you so
Okay.
much. Is it okay? I ask your permission. Is it okay if I upload it into YouTube? Then I share
Sure,
with the
sure.
president. Okay, that's
Sure,
great.
sure.
Okay, thank you.
Okay, thank you, doctor, for
You're welcome.
your time.
Thanks
you,
a lot
doctor.
for asking.
Although it's holiday today.
Yeah, don't worry. Happy Vesak Day to both of you.
Same, doctor.
All right.
Thank you, doctor.
Thank you,
All right.
doctor.
Take care. Bye.
Bye bye.
Bye, doctor.
Yeah, bye.